Welcome back. Today we're going to talk about teen driving premiums. Now before we get into the activity itself, we're going to take some notes on applying composition of functions. Now composition of functions I often look at kind of like nesting dolls. Those dolls where if you open them up you find another doll inside, and then that kind of keeps happening and you have like 5 dolls within another doll. Composition of functions is very similar to that. So let's take a look at this example and see how we could actually use composition of functions to build larger and better functions to represent what's really going on in the situation. So in the mail, you receive a coupon for $5 off a pair of jeans. Now that part would mean that we actually get to subtract $5 from the price of the jeans. Pretty cool. Now when you arrive at the store, you find that all jeans are 25% off. That means you can take 25% of the current cost off of the jeans, leaving you paying 75%. So 25% off means you pay 75%. Because your percents have to add up to 100% for the 100% of the cost. So now let's look at what we're going to do with this. Let x represent the original cost of the jeans. Write a function f of x that represents the effect of your original coupon. So our original coupon was this $5 off. So my f of x function is going to be the cost of the jeans minus the $5 that I don't have to pay. That's my function. For the next part of this, write a function g of x that represents the effect of the 25% discount at the store. And as I said before, if you get to deduct 25% of the cost of the jeans, then you have to pay the remaining 75%. And 75% as a multiplier would be 0.75 times the cost of the jeans. Now another way to look at this is if you take the entire cost of one pair of jeans and you're allowed to subtract 0.25 of the cost of that pair of jeans, 1 minus 0.25 is actually 0.75x. When this simplifies, it becomes what I described to begin with. So this is why looking at what it takes to actually add up to 100% of the cost works to help you kind of shorten the process in finding this equation. Now for step 3, we're going to write a function h of x that represents how much you would pay if you use the mail coupon first, followed by applying the discount from the store. So we want to use this function first, followed by this one. So what we're doing is we are taking our functions and we're kind of nesting them. So g of f of x, which is actually g of x with f of x nested inside of it, because what's inside is what you do first. And then you kind of build outwards from the inside of your parentheses as you're working out a problem. So if f of x is to be done first, it needs to go into the parentheses inside of the other function. So let's take a look at this. We have f of x was x minus 5, g of x was 0.75 times x. I want to do this first and then apply that 0.75 to the result. That's why I'm saying that f of x is going inside of g of x for g of f of x. So h of x can be written as 0.75 on the outside, but instead of x, now we're going to use x minus 5 within that. So f of x is done inside the parentheses first to calculate the new cost of the jeans that I then take 75% of to figure out how much I actually have to pay with that 25% off discount. Right, now this next section, write a function j of x that represents how much you would pay if you use the store discount first, followed by the mail coupon. So now we're going to reverse this. We're going to take f of g of x. So f is on the outside now, and g of x is what we're doing first on the inside. So let's take a look at this conceptually. I have f of x, which is x minus 5. I have g of x, which is 0.75x. I want to take that 25% off discount first. So I'm going to take this, and then I'm going to use that -5 coupon. So this 0.75x is having to go in and replace the x right here, which is why I'm taking f of g of x. So g of x is replacing my x in f of x. And that's why we changed the letter at the beginning of our function, to show that we've actually done something completely new. So I'm going to have 0.75x and then -5. So I'm taking that 25% off, then subtracting the 5. Notice that the only difference between these two is a set of parentheses. And that's really important. Order of operations is vital whenever you're working out a set of numbers. Here I would have to subtract the 5 first. Here I would subtract the 5 last, all because of these parentheses, and that's determined by which function replaced the x in the other. Now let's take a look at what effect this really has. So you find a pair of jeans for $36. How much would you pay for it using both of these functions, h of x and j of x? So for h of x, I would figure out 75% of the cost after I subtracted 5 from that 36. So I take off my $5 coupon, which gives me 31, times the 0.75. And so h of 36 is going to equal let's see, 23.25. So $23.25 is what I would actually be charged. Now up here, I'm going to fix my notation. Since I substituted the 36 into this equation up here, I really should have 36 replacing my x right here. All right, let's look at the other way of doing these discounts. So I have a pair of jeans that's $36, and I'm going to apply the j of x function to that $36, which means I'm going to take 25% off, so I'm only paying 75% of the 36, and then I'll subtract the 5. So 36 equals, so 0.75 times 36, and then -5 gives us 22. Now, this is the reason that typically you end up with all of your different deductions going through, and then they'll actually take off the percent at the very end. So usually they take off whatever money first and then take off the percent, because that's what's going to get you to pay more. So stores will rarely follow this sequence. They'll usually follow this one. All right, now if you only have $40 with you, what's the most expensive pair of jeans you can purchase? Now that's going to depend on which formula we're following. So let's try this both ways. All right, so the first way, the $40 is what we actually hand the cashier, so that's going to be the result of h of x or j of x. So instead of replacing x, this time we're going to solve for x. All right, so my original function, h of x equals 0.75 times x minus 5, and 40 is going to replace that whole thing. And now I go through and I solve. Now instead of distributing this, I'm actually going to divide this multiplication off, because if I divide it, then I won't have to worry about these parentheses. The only reason those parentheses are there is because of this multiplication. So undo the multiplication and you don't have to worry about the parentheses. So 40 divided by 0.75 is about 53.33, and that is still equal to x minus 5, because 0.75 divided by 0.75 canceled out to 1. And 1 times x is x, and 1 times -5 is -5. Now, to undo my -5, I need to add 5 to both sides. So I have 58.33 equals x. And this is the highest price that I could actually afford for a pair of jeans. I could afford less than that, or I could afford this. Now that's if they subtract the 5 first and then take off the 25%. Let's see about the other way. 0.75x minus 5. So again, I'm going to replace j of x with 40. This time I have to add the 5 to both sides because I don't have parentheses allowing me to remove the multiplication first. So I have to go in my reverse order of operations and undo addition first. So I have 45 equals 0.75 when I simplify that out. And now I can divide by my 0.75. When I complete that, I get x equals 60, so $60 is the most that I could actually afford for a pair of jeans with all of the discounts that I would get. So while we prefer for them to calculate it this way, most stores will calculate this way because they'll make a little bit of extra money even though it looks like it's the same deal. And it all depends on how you actually put the functions together, what the composition is of the function. All right? So let me know if you have any questions, and I will see you in class.